Hey, everybody, and today we're going to be working on 6-1, which is the standard normal distribution. Okay, and basically in here we have these key concepts. In this section, we present the standard normal distribution. So this is just the standard normal distribution, which is a specific normal distribution having the following three properties. It's very important. It has a bell-shaped curve, and bell-shaped curve would look like this. And it could be like this. It could be long and skinny, but it always has that bell shape, okay? The mean is always 0, and the standard deviation is going to be equal to 1. So we're going to develop the skills to find the areas or probabilities or relative frequencies corresponding to various regions under the graph of the standard normal distribution. And we'll also talk about the z-scores that correspond to the area under the graph. So basically when they're talking about is, let's say I have this, let me make this a little bit better. Let's say I have, here's a normal curve. It's not much better. But if I want to know, let's say right here is where my point lies. Well, I'll explain more about this later. Then the area under the curve from here to the end would be the same as my probability. The area under the entire curve is 1. So that's how we're going to find probabilities, because remember, probabilities are between 0 and 1. So we use this normal distribution. Oh, here's a better picture. You don't really have to worry about this. You won't be using it. But that's the equation for this curve. So normal distribution, if a continuous random variable, so these are important points, continuous random has a distribution with a graph that is symmetric and bell-shaped, just like it is here, we say that it has a normal distribution. So we're going to start off talking about uniform distribution, which is a little different. The area under the curve, so the area under the graph of a continuous probability distribution is still 1, because otherwise it wouldn't be a probability. Remember, probabilities are between 0 and 1. There is a correspondence between area and probability. So probabilities can be found by identifying the corresponding area in the graph using this formula for the area of a rectangle. So here's a formula for the area of a rectangle. For uniform, we can use exactly that, okay? Because you'll see in a second. A continuous random variable has a uniform distribution if its values are spread evenly over the entire range of possibilities. The graph of a uniform distribution results in a rectangular shape. All right, density curve. The graph of any continuous probability distribution is called a density curve, and any density curve must satisfy the requirement that the total area under the curve is exactly 1. Remember, we have to have, if we're going to say probability is related to air, it's related to, is always between 0 and 1, then we say that that's related to the area under some curve. That curve has to have area between 0 and 1, right? It can't have an area of 2. What would we do with that? That wouldn't correspond directly with our probability. So because the total area under any density curve is equal to 1, there is a correspondence between area and probability, just like I just said. Okay, here's a good example. Waiting times for airport security. During certain periods of time at JFK Airport in New York City, passengers arrive at the security checkpoint having waiting times that are uniformly distributed between 0 and 5 minutes. So here we have, so uniform means that the probability of any value between 0 and 5 is 0.2 or 20% between 0 and 5 minutes, okay? Then all of the different possible waiting times are equally likely. Waiting times can be any value between 0 and 5. So it is possible to have a waiting time of 1.23456 minutes. Depending on how many decimals we can carry it out to, it's a continuous graph because every value is possible. By assigning the probability of 0.2 to the height of the vertical line in the figure, the enclosed area is exactly 1. So how would we find that? Remember, the area under a curve is equal to the length times width, or you could also say the base times the height, whichever way you like it. So if I know the area is always 1, and I know the base here is 5 because it's between 0 and 5 minutes, and we want to figure out what the probability is, we can divide both sides by 5. 1/5 is the same as 0.2 equals the probability of any event happening. Okay, so that's how we get that value. And basically it says that kind of right in here. We say, in general, we should make the height of the vertical line, or the probability, in a uniform distribution equal 1 over the range. And what we're saying is the range is 1, 0 to 5, which is 5 minus 0 is 5. All right. So given the uniform distribution illustrated in this figure, find the probability that a randomly selected passenger has a wait time of at least 2 minutes. So we're saying it's anywhere between 2 minutes and 5 minutes. So really we're looking for this area. At least 2 minutes is 2 or more. And the most what we were told was 5. So if I want to find the probability, I multiply the base, which is 5 minus 2, times the height, which is 0.2. So this is 3 times 0.2, which is equal to 0.6. Or you can say 60%. Okay, so there's a 60% chance that a passenger is going to wait at least 2 minutes, which means there's a 40% chance that the passenger will wait less than 2 minutes, right? 1 minus 60% is 40%. 1 minus 0.6 is 0.4. So now we're going to talk about standard normal distribution. And that's like we were talking about uniform distribution. So the standard normal distribution is a normal distribution with the parameters of mu equals 0. So notice that's right here in the middle. Sigma, which is the standard deviation, mu meaning the mean, so the standard deviation is 1. So this is 1 standard deviation, 2 standard deviations, okay? And the total area under the curve is 1. So this goes right along with our probability. And we do use this for probability. Okay, so finding probabilities, if you're given a z-score, we can find areas, which is exactly the same as a probability, for different regions under a normal model using technology or table A-2. I'm going to show you a table I don't recommend you use the tables because I'm going to also show you how to use StatCrunch. Technology is strongly recommended because calculators and software generally give more accurate results than a table. We strongly recommend using technology, which is what we will be doing. We'll be using StatCrunch. Okay, finding probabilities when given a z-score. So if we look at the table here, let me pull up a table here for you. So you just have an idea in case one day you need to use a table for something. So here, notice we have, this is a standard normal distribution table. And if you look at this picture, you can see that it's always from the z number, which is over here on the left, to, and it's everything to the left of the z number. So and we're looking at the area under the curve. Okay, so let's go back here. Table A-2 is designed only for the standard normal distribution, which is a normal distribution with a mean of 0 and a standard deviation of 1. So this is important. Okay, so for a standard normal distribution, it has to have a mean of 0 and a standard deviation of 1. There's going to be two tables, two pages to the table, one for the negative scores and one for positive z-scores. Each value in the body of the table is the cumulative area from the left to the vertical boundary above a specific z-score. Well, I'll show you what all this means. And when working with a graph, avoid confusion between z-scores and areas. This is important. So z-score is the distance along the horizontal scale of the standard normal distribution, which corresponds to the number of standard deviations above or below the mean. And then the area is the region under the curve, which is our probability. So let's take a look. So if I say I have a z-score of, let's say, negative, hold on. Let's say we have a z-score of negative 2.57, okay? So let's see what we do. This is really not a necessary thing, except maybe it'll make it easier for us to see. Yeah, maybe. Okay. So this is the table, and let me move the z-score that we picked. So we picked negative 2.57. So what we do is we go down here and we see negative 2.5, and then we go over until we see this column here. Here, let me. So this column here, so we have negative 2.5, goes all the way across here. And if I want 0.07, notice here's 0.07, so I would look down this column. And I notice where this column, yes, I can, hold on. See if I can make this a little wider. No. Okay, so this column right here is the 0.07 column. And so where they intersect is 0.0051. That would be our probability, which is the same as the area under the curve. Okay. And then we would have the same thing in the if we had picked a positive value. So for example, if I pick positive 2.57, let's see if we can do this without downloading it into StatCrunch. So we go down here, there's 2.5 right there. Here, let me highlight it. So here's 2.5. And then we have to find which column is the column with the 0.07. I mean, you can see that it's not as easy as, let's see, this is the column right here. So in this column, we're right here. Oh, right where that dot is. Okay, that's easy. So I'll go across and I'll say, oh, that's not what I wanted. I'll say right here, that's my probability that my value is less than or equal to 2.57. Okay, so that's the probability. That's basically, if we look at this curve, we would have our z-score further out, right? So it would be somewhere around, probably somewhere right out, this far out even. And it would correspond to all this area to the left of that point if I was looking at my z-score of 2.57. I would have a probability of, now everything's moved, but I think it's 0.9949 right here. Okay, so that's basically how you read the table. Are you going to read the table? No, we got everything in StatCrunch. No worries. Erase all that. And we'll get to this problem in a little bit. First, let me talk more about normal standard normal distributions. All right, so we have here a bone mineral density test can be helpful in identifying the presence or likelihood of osteoporosis. The result of a bone density test is commonly measured as a z-score. The population of z-scores is normally distributed with a mean of 0 and standard deviation of 1. Perfect. I know now that this is going to work, so that these test results meet the requirements of a standard normal distribution. The graph of the bone density test scores is as shown in this figure. A randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density test score less than 1.27. So we've already seen how to use the table. Let's see how to use StatCrunch. All right, so I am going to come here and I'm just going to open StatCrunch. That's the only thing I'm using those problems for at the moment. And I want to know, so I want to hit Stat Calculators Normal, because we have a normal distribution. My mean is 0 and my standard deviation is 1, which is perfect. And this is basically where I put my z-score. So I want 1 less than or equal, because it says right here, probability that this person has a bone density score less than 1.27. And over here, I get my probability. And you can see if I round it to 4 decimal places, it's 89795, which would round up to 8980, which is exactly what this says here as far as the area under the curve, which they got from the table. We got it here from our StatCrunch, okay? Same exact thing, there's nothing to say here. Interpretation. The probability that a randomly selected person has a bone density test result below 1.27 is 0.8980, shown in the shaded region. The shaded region, they're talking about this shaded region. Another way to interpret this result is to conclude that 89.8% of people have bone density levels below 1.27. That's it. That was all we had to do, is go into StatCrunch, go into calculator, stat, normal, and it gave us everything we needed. So now what if we want to use the same information, but we want to find the probability that a randomly selected person has a result above -1. Okay, so we'll go back, pull up StatCrunch, and stat, calculators, normal. And we can really put in whatever we want. So if we want above -1, that's my z-score. That's not my probability, right? So I put -1 in here, but I want it to be greater than or equal. And I get, yes. So here's my value, and I get 0.8413, which is exactly what it shows right here for z equals -1. This is the normal range of bone density readings, okay? If I want to see, let's see, what else do I have here? Let's just make this a little bigger so I can see what we're doing. So if it was less than or equal to -1, okay, let's see how to do that. So we have less than or equal to -1. Now this is to the left of -1, because here's 0, so this is -1, and we have 0.158 or 1587. Here, this is, well, this is the same as what we got here from the table. So you could do that, or you could even say between two values. We'll get to that in a little bit, okay? Actually, we'll get to it right now. So, example, bone density test, finding the area between two values. So a bone density reading between -1 and -2.5 indicates the subject has osteopenia, which is some bone loss. Find the probability that a randomly selected subject has a reading between -1 and -2.5. So again, I go into my StatCrunch. I can close it. I'll close it and open it back. So I have stat, calculators, normal, and I want my values to be between. My lower limit is 2.5, -2.5, and my upper limit is -1. I hit compute. Notice that red line now is not going all the way to the end. It's just going between -2.5, which is right about there, and -1. And the probability of that happening is 0.1524 or 15.24%, however you want to look at it, okay? Which is exactly what this says. Only if you had the table, what you would have to do is find the area to the left of -1. So you would start with this value. Then you'd find the area to the left of 2.5, and you would have to subtract. You would have to subtract this area from this area, because this area is going all the way to the end, but I want to take off this little piece here at the end, which is from z equals negative 2.5. So that gives me my area of 0.1525, which is actually a little higher, because this is from the table, than what we actually got. Okay, but really close. Interpretation. So using the correspondence between probability and area, we conclude there's a probability of 0.1525 that a randomly selected subject has a bone density reading between -1 and -2.5. Another way to look at it is to say that 15.25% of people have osteopenia with bone density readings between -1 and -2.5. So, that was helpful if that's what you're looking for. Different notations. So basically, this is saying we want the probability that our Z number is between A and B. Okay, so we would write it like this: A is less than Z and Z is less than B. This, of course, is Z is greater than A, and this is Z is less than A. So it's just different notation for whatever we're looking for, and I'll do some example problems, not to worry. So now we're going to talk a little bit about critical value. For a standard normal distribution, a critical value is a z-score on the borderline separating those z-scores that are significantly low or significantly high. The expression z sub alpha denotes the z-score with an area of alpha to its right. So this is very important because we're talking about a z-score to its right, which is different than what we would get from a table, right? Remember that z-score is always, not the z-score, the area is always to the left, but this is to the right. So for example, if I want to find the critical value z sub alpha, and it says find the value of z sub 0.025, that means alpha is 0.025. So I would literally just go into my StatCrunch, and I would say, well, I don't want between, I actually want greater than, because I want it to be above that number. But that number is my probability, okay? So this alpha is my probability, and I want to find the z-score that goes with it. So I put my probability where my probability would be. And I hit compute, and it gives me my z-score. So I can go either way. My z-score is always in this box. Oh, sorry about that. So my z-score is always going to be in this box. And my probability is in this box. Okay, so that's basically how you use the normal calculator. And we got the same values for sure. Oh, okay, so that's the end of the slide presentation. Now let's go do some of these problems. So question number 1. I'm going to put that over to the left. And I want to put my StatCrunch over here towards the right. and we'll close it up. A statistics professor plans classes so carefully that the length of her classes are uniformly distributed. Now that's a very important thing, uniformly distributed between 50 and 60 minutes. Find the probability that a given class period runs between 50.5 and 51.25 minutes. Now this is not a standard normal distribution. This is a uniform distribution. And the lower limit here is 50 minutes. The upper limit, 60 minutes. And I want to find the probability that the given class period is between 50.5 and 51.25. And I hit compute. And this is my probability right here. It says round to 3 decimals. That's what I have. Let's copy and paste. And check our answer. Perfect. Okay, not too bad, right? Now we have a normal distribution curve. Find the area of the shaded region. The graph depicts the standard normal distribution with mean of 0 and standard deviation of 1. Let me open this up a little bit. Okay, so now we could use the table. If you like, you're very welcome to use the table. I'm going to prefer to use StatCrunch. And I go to normal. And I know my Z number. If I put my Z number in here, and hit compute, this is the area of the shaded region. Notice that's the one we want. We want the one to the left. So it says round to 4 decimal places. 1, 2, 3, 4. After this is a 1, so I don't round up. Pop it in there. And we'll check our answer. Perfect. Just as a note, the middle here from at 0 to the top, this right here should be a straight line. Everything to this side is 0.5 or 50% of all our data. And to this side, it's also 0.5 or 50%. I know you can't read that. But notice if I add them together, I get 0.5, 0.5 plus 0.5, which is 1, which is my probability is always between 0 and 1. So if I look at the entire graph, then it is 1. Half of it is below 0, half of it is above 0. So here for this, all I do is find the indicated Z-score. Okay, so now they're giving us not the Z-score, they're giving us the area under this curve. And they want us to return to them the Z-score. So I'm going to put in here, in the probability side, for this, which is the same as the area side, 0.9678. And I want it to the left because that's going to give me my Z-score. I hit compute and my Z-score to 2 decimal places would be 1.8. The next number is 9, so it's going to round up. So this is going to be 1.85. And I check my answer. Perfect. I want you to notice that I'm looking at the area in here, which is what this red represents. If they wanted this little bitty area here that I'm pointing to now, I would have to say greater than, this is my z-score, and I would hit compute, or let's just make sure it computed properly. Yes, it did. And if I add this number, no, never mind. Oh yeah, no, if I add this number here, which is my probability, to 0.9678, we should have 1, because that's the total probability. So if I add the area on this side plus the area on this side, it's 1. When I make it less than, notice this where most of the area is. Okay? And they're going to always give you these tables. You don't need to use them. And notice I'm going from problem to problem without closing StatCrunch, because what's the point of closing it? I'm going to need it again anyway. Now it says find the indicated critical value, and it's Z0.11. So that's alpha. And if you remember, we're always looking to the right of whatever our alpha is. So that's our probability. That gives me 0.11. I hit compute, and now I can find my critical value, which is my z-score. And we're going to round that to 2 places. So it's going to be 1.23. And I hit check answer, and I'm done. So as you can see, there's really not much to calculate here at all. We use StatCrunch, we get our answers, and that's really all we have to do here for this section. And I think that's all I have to say. That's the end of the video. Thank you for watching. See you soon. Bye.